Okay, so there again, the reason why OR is more nucleophilic or more basic than OH is because OR has an R group. It's an alkyl group. No, it's an alkyl group, which can have RO, an electron donating inductive effect. I've mentioned earlier that there's two types of inductive effect, but in the case of R, it's an electron donating inductive effect. I-induce niya ang silingan niya to have, and so to acquire or to have also an electron density, to share its electron density sa silingan, that's induced an inductive effect by electron donating. Okay. And so that's the reason. Now the question is, you also have an R here and CO2. Why would it be less basic than your OR here? Again, the reason is of the C double bond O. The C double bond O would have as C double bond O. You have R, C, double bond O. Or is O here, and that, and of course you have negative charge here, and oxygen will also have negatively charged. Now, when you have a double bond, of course, and naakay silingan ng atom, adjacent atom that has an electron pair, it will always have a resonance structure. And having the resonance structure, it could also stabilize your system. Okay. So you will have a resonance structure, and you will have R, C. So how do you form the resonance? Okay. So here, it will disperse its negative charge here by sharing the electrons to carbon and form a bond, and then your double bond here would go to oxygen. So in effect, you will have O, so see oxygen here, first oxygen will have the double bond will be converted to an entered electron. It will bear a negative charge, and the second oxygen will now bear a double bond with two dots. Okay, and so you notice that the electron shared in COO is actually between the oxygen here and here. So there is what you call as a resonance structure, and will stabilize the COO here. Okay, so the electrons are shared between oxygen, carbon, and here. In fact, when you write the structure of this, the resonance form, the hybrid of the structure 1 and structure 2, no, it's always that R, C, O, and there is that partial negative. So there's two negative, 1/2, and negative 1/2 for the two. Of course, the electrons, there's electrons here, but the other electron will always be shared between these two atoms. And this is what you call as your resonance hybrid, the hybrid structure of 1 and 2. And because of this resonance structure, it stabilizes the resonance structure. The resonance stabilizes the base. Somehow it stabilizes the base or the nucleophile. Okay, so since the electrons are, we call it delocalized, and the electrons are delocalized, which means that at some point, okay, at some point, the electrons of one of the oxygen will go to this first oxygen, and then the next time it will go to this, and the probability that you can find that electrons is between these three atoms here. Okay, it's delocalized. It's not only like compared here that the electrons that will be shared or that can be donated is na lang sa oxygen. In this case, the electron that will be shared or that will be donated to the positive carbon, to the other center, positive center, is delocalized, no? So sa Bisaya sa delocalized, nagkuan siya, naglihok siya, no? There's this delocalized, no? It's between this region, between this atom, dili lang siya din ha. Pag sa oxygen lang siya, it's called localized, no? Oxygen alone. But here, the electrons are delocalized. It's shared among these three atoms here. Okay? So, hanap ko. Okay, so what else? And then of course you notice here that the first three has a negative charge, and from negative one. From the first statement, the strength of the nucleophile will always be high when your nucleophile is negatively charged. So the first three are negatively charged and the last two are neutral, no? And between ROH and water, of course, there is an R here, and whenever you have an R, it will have again an electron donating inductive effect. So it will strengthen the electron density of oxygen. So here is compared sa hydrogen here lang, water. No? And therefore this ROH becomes...
wala yung makita nga presentation, ma'am.
How about now? Ana?
Okay naman.
Okay, so here, again, here you have an ROH, no? So the difference is an R. There is an R group, which has a property that would donate electrons by inductive effect. So really good in reality, no, nga would donate just like a base acid reaction, but i-induce lang niya yung silingan nga atom with its electron density. So more enhance niya yung electron density of oxygen so that it can more give electrons sa another positive center. So compare nimo kang water. Okay, so that's the second consideration when we're talking about the nucleophile. First should be negatively charged, is more nucleophilic, and it's more nucleophilic in a group of nucleophiles. In each nucleophile, it's the same nucleophilicity, parallel basicity. So this 1, 2, 3 are more basic. No, they can donate more electrons. Basicity and nucleophilicity are the same. So can define, you can go on the definition of a base, the Lewis base, and the definition of the nucleophile. They are quite similar. And when the nucleophilicities, so nucleophilicities, when we're talking in terms of nucleophile, basicities, when we're talking about in terms of the substance being a base. No? So you always have again to think of the definition of a Lewis base. So here is the order of the basicity. Okay, here is the order of basicity, and this is also the order of nucleophilicity. Okay, so OR is more nucleophilic than OH, then RCOO minus, then ROH, then H2O. OR is more basic than OH, then RCOO2 and ROH. So this is the kasabot aning parallel. Parehas ang trend sa being this substance as a nucleophile and this substance as a base. Nasabtan ba ko? Now, when the substance, when the nucleophile atoms are different, so in this case, the nucleophile here is sulfur. Here you have carbon, the electrons. Carbon, yes, the nucleophile here is carbon, you know, carbon man. The nitrogen here is neutral, no charge. Carbon here is the one that's negatively charged. Okay, and by the way, it depends, no? And also iodide, iodine, and OH. So when the nucleophiles are different nucleophilicities may not parallel basicities. So for example, kapag lahi-lahi siya, marag lisod siya i-predict, no? But generally, we can have a trend. sulfur carbon IDOH here. For example, in protic solvents, HS or bisulfide here, bisulfide. The sulfide, HS minus, CN, cyanide, and they're all weaker bases than OH. So HS and I are weak base than OH, yet they are stronger nucleophiles than HO. So which means when you say stronger nucleophiles, they can easily attack a positive center. Whereas when you say strong base, they always can readily namanggoy strong base can donate, would have a greater tendency to donate electrons. When we say nucleophile would have a greater tendency to attack a positive center. So for a nucleophile to attack a positive center, dapat na siya electron density, na siya unshared electrons, and should also be a negatively charged. So in this case, no, even if HS, S minus, CN, and I, they are weaker bases than OH. Ganun weaker bases pa siya. So this is sulfur, and here CN and I, there are I and sulfur, no. There are large atoms, no. You can find them in group sa ubos na in the per family, and because of that, the negatively charged, the electrons are easily dispersed, can be dispersed and stabilized. Okay, so therefore they are less basic than OH. And CN code here, you see here there is a triple bond, so there is a possibility of a resonance here. So si nitrogen can bear some of the electrons and so on. Okay, iodine here. So when the nucleophile atoms are different, nucleophilicities may not parallel basicities. So here, since you consider this one to be more nucleophilic than OH, then they can easily attack a positive center. So maski pa si OH, the hydroxide is more basic, has more tendency to donate its electron pair. So how do we differentiate nucleophilicity versus basicity? I've already mentioned. So while nucleophilicity and basicity are related, they are not measured in the same way. So as I mentioned already, nucleophilicity is measured by the relative rates of substitution reactions. Kana bitang nucleophile siya, so dali siya mo attack sa positive center, dali siya mo attack sa positive center, paspas ang reaction. So the nucleophilicity is measured by the relative rates of reactions. So in particular, when we are talking of the substitution reactions, such as an SN2 reactions, no. So kung dali na siya maka-react, no, maski pag dili kaya siya basic, but dali siya maka-react, therefore it is more nucleophilic. So this is the case of HS here. No, dili kaya siya basic as your OH. If you compare HS and OH, okay, but they are more nucleophilic. Okay, so basicity is expressed by pKa. It's measured by measured by the position of the equilibrium. But when we, yes, this is by the definition of the Arrhenius acid-base reaction. But in the Lewis definition of basicity, always have to remember that the Lewis base is always the substance that always donates its electron pair. So whatever factors also that would make it, that would allow it more enhance its availability of electrons, then that substance will be more basic. Okay. So let's consider this one. Rank the following 6.11. So your problem set is 6.11. I have to compile which one. Rank the following in terms of decreasing nucleophilicity. So CH3, so O minus which one would be more nucleophilic? Do you think which one? So since you've seen here that some of the 4 of the nucleophiles here have the same atom. That would be the nucleophilic atom. Okay, it's oxygen. So which one do you think will be the most nucleophilic? Which one do you think can easily attack positive center? Which one? Oh my God. Which one? H3CO2. Of course, you always have to choose the one for oxygen and oxygen. First, you always have to think of oxygen, no? The more negatively charged, right? So you choose on the more negatively charged, CH3CO2 or CH3O. Asa man sa ila duka. There's only two. Which one do you think will be more nucleophilic? CH3CO2 or CH3O? Anyone?
CO2.
CH3, CO2, CH3O. Okay, you have to remember that whenever you have CO2, no, there is C double bond OO. So there is that resonance structure, right? So when I say there is resonance, the electrons are delocalized throughout. So magbalhin-balhin siya, and it gives more stability to your COO, to your compound. So because it is stable, it's not easily actually, because the system or the substance is stabilized by electron delocalization, by resonance. It's not actually easy to give the electrons to the other substance when there is this resonance structure. And that is one of the reasons that dili siya more basic, dili siya basic, mas more basic when there is no resonance. Whenever there is a resonance structure, no, it can stabilize the substance. And when it undergoes stabilization, the electrons involved in the delocalizations cannot be easily be donated, no, as compared kung walay electron delocalization. Stabilized man siya, so dili wala siya need to disperse the negative charge sa iyahang. Ano man, it's already dispersed within its system, kaya na siya delocalization, na siya system, na siya mechanism, let's say mechanism to stabilize the negative charge by delocalization. Compared mo sa, for example, walay delocalization, walay resonance, so it has more need, no, to disperse the negative charge by forming a bond. Okay, when it forms a bond, of course, mahiwa na siyang neutral. Okay, so we'll be looking at the negatively charged species, CH3CO2 or CH3O. But there is this nitrogen, so CH3OOOO. So you notice the difference between nitrogen and oxygen. Let's go back to the periodic table, NOF and NOF. So which one is more electronegative, nitrogen or oxygen? And here you also notice on this NC33, N triple bond C, that it's a linear, no, there is no obstruction of the electrons in the NC, N triple bond C. Okay, so it can easily donate its electron density as compared to NOF. And also, if you compared on the electronegativity between nitrogen and oxygen, you will notice that oxygen is more electronegative than nitrogen. Okay, and being that kinsa may mas would have more ability to donate the electrons, no? Nitrogen being less electronegative than oxygen, so it will have more tendency to donate electrons. Kaya kung si oxygen, na siya more tendency to draw the electrons to itself compared to nitrogen. So because of that, you have to consider the one with the N to be more nucleophilic, more ability to attack and donate. And also another reason is it's a linear substance, no? You can see on the structure, it's linear. And so it can easily be compared here that here it assumes the V shape. Assume for the, or sp3, no, sp3 hybrid orbitals. Here it assumes the sp also orbitals. And C here would become the more nucleophilic, more tendency to donate the electrons. And then here, compare the CH3COOO and CH3O. CH3O will be more nucleophilic than CH3CO2 because, again, I've mentioned earlier, this one can be more stabilized because of the resonance structure or resonance stabilization or electron delocalizations compared here. So the other one, they are of course, I notice a negative deletion. And this one, the other neutral nucleophiles are the least nucleophiles. Okay, as compared to the three. And between CH3O and CH3COH, you consider them to be more nucleophilic than this, again, for reasons. This one is more stabilized by delocalization or resonance stabilization. And okay, so there is less availability of the electrons to the positive center. Okay, let's go to the effects of solvents in the SN1 reaction. So we have already considered the effects of the substrate, second, the effect of the nucleophile, and third, we will consider on the effects of the solvents in the SN2 and the SN1 reaction. So for SN2 reactions, it is favored by polar aprotic solvents. So instead ng aprotic without proton, no? Without proton. Sabi ng proton, katong H+, no? Where you can find the H+, like water, CH3O, CH3 methanol, you can find the H+. So aprotic kana without proton. Example is the acetone. Sa gani ng acetone, acetone is CH3, C double bond O, CH3. DMF is dimethyl for, I think I have written the structures here. Here. So you have here the acetone. Okay, you have the dimethyl sulfoxide, S, dimethyl sulfoxide, SO, and DMF, dimethyl formamide, dimethyl, NN, dimethyl, so NN dimethyl, so it's connected to nitrogen, NN dimethyl formamide, 1, 2, amide, 1, 2, formamide, okay, and HMPA, the hexamethyl, 1, 2, 3, hexamethyl phosphoramide, double bond ON, phosphoramide, amide, double bond ON. Okay, so for SN2 reactions, it favors polar protic solvents, I have already mentioned. For SN1 reactions, it favors polar protic solvents, like for example, ethanol, methanol, water, whenever there is an alcohol or there is water in it. Okay, so important reasons for the solvents effects have to do with minimizing the solvent's interaction with the nucleophile in the SN2 reaction. So if you remember that in the nucleophile SN2 reaction, there is this concerted reaction of attack of the nucleophile to the positive center of the substrate, and there is a simultaneous leaving of the leaving group, of course, in the substrate. It's very simultaneous. So in the presence of a protic solvent in the SN2 reaction, it will there is a possibility, that it will affect and or hinders, or reacts with the nucleophile, the presence of a protic solvent, So we want to minimize the solvents interaction. Of course, we want to minimize the solvents interaction such that what is being promoted is only the reaction between the nucleophile, of course, and the substrate. Second reason is, of course, in the SN1 reaction, the presence of a protic solvent will facilitate on the ionization or stabilizing the ionic intermediates of the solvent. So when the leaving groups leave, The presence of protic solvents can actually stabilize the leaving group when it leaves the substrate. So we'll explain more later. So in the SN2 reactions, whenever we use this kind of solvent, acetone, then as I mentioned, the polar protic solvents, the reaction actually is vastly increased. The SN2 reaction is more dramatic, mas paspas, mas taas yung rates of reactions compared when we carry the SN2 reaction in polar protic solvents. It's like millionfold. So what happens when we use polar protic solvents, and in the SN2 reactions? So here is an example of the polar protic solvents, like dimethyl sulfoxide, as double bond O here. Okay. So the polar protic solvents solubilize the cations, just in the illustration here. For example, the base is the sodium iodide. And what happens is that these aprotic solvents will solubilize the cations, meaning the counter ions of the base, but do not interact strongly with the anions because they cannot form hydrogen bonds. So since they usually this aprotic solvents actually have very high dielectric constant. It's very, very polar, in such a way that they can readily form ionic interactions with the ions here, like such as the cations. So, and because of this interactions of the solvent, the aprotic solvent with the cation, so the nucleophile is more exposed. Wala na siya close, walay ka ng counter ions nga close sa iya, that it really has more need to attack the substrate. So this differential situation leaves an ions more freely to act as nucleophiles because they are less encumbered by the cation. So usually good in normal settings, this iodide will always be silingan. There's always this counter ion that will be close to iodide. But of course, when we use an aprotic solvent, we will expose more the nucleophile by the interaction by surrounding the cations or by increasing the interactions of the cations and the solvent. Okay, now let's consider, so what happens, I mentioned, when the counter ions of the iodide ion, our nucleophile, for example, is being surrounded by the solvent, the iodide, the nucleophile, in this case, iodide, can be more exposed to react with the substrate. So when I say more exposed, kaya wala naman siya silingan, the counter ion that could help disperse its negatively charged, this anion or this nucleophile, running out of time, 10 minutes. Okay, this iodide, I really hate Zoom now because it seems like we always be cut by the time. Anyway, so moving on, the iodide, without having these counter ions, katong silingan yung ions that could disperse its negative charge, it's more naked, it's more exposed, that its only way of dispersing is charge. Kay dili man siya ma-disperse, dili man siya mas-dispersing negative charge by the cation, kaya nga naman, it's already being surrounded, it's already being interacted with the solvent. Its other option is to attack the substrate. So there will be an enhancement on the substitution reaction. Next. Ano man eh? Okay, where am I? So here. So in this naked anions in polar aprotic solvents are also more reactive as bases as well as in their capacity as nucleophiles. In dimethyl sulfoxide, DMSO, for example, the relative order of halide ion basicity is the same as their degree of nucleophilicity. Okay. So the trend is that if you remember your group 7, fluorine, chlorine, bromine, iodine, so fluoride ion is more nucleophilic than chloride, than your bromide, than your iodide. So this is also the same order as its basicity, no? Fluoride has more tendency to donate electrons as a base than chloride, than bromide, and iodide. Why is that? The larger your ion is, your anion, the more it can be stabilized, no, by polarization. So the reason for stabilizing is polarization of its electron density. The larger the ion is, okay, the more stabilized it is now by polarization. So the smaller the ion, the more nucleophilic it is. So like chlorine is more smaller than chlorine. Of course, even if chlorine is more electronegative than chlorine, now it's having this different size, group 7, fluorine will have more tendency to donate its electron pair than chlorine, than bromine, than iodine. Why is that? It's a small ion, and it's hard for fluorine to disperse its negative charge, and it would rather react rapidly with a positive center, no? Or it will rather react with a Lewis acid, wherever it can disperse or donate its electrons. As compared to iodide, for example, which is a large ion, this charge sa ion can be easily dispersed by polarization. It's a big ion man, so it's compared to a small ion. Okay, so the size of the anion can actually affect on the relative basicity and the relative nucleophilicity. So in this case, the order of nucleophilicity is also the same as the relative order of the basicity. So inani po the order of them being a base. Next. So what happens, if we use protic solvents for an SN2 reactions? The truth is the presence of protic solvents actually also hinders the nucleophile in attacking the substrate. No, for example, we have our nucleophile here, or halides, like X minus, no, with electrons in the presence of a protic solvent. Let's just say water. No, there is proton here. This anion, this halide, which is also our nucleophile, no, can be stabilized by the presence of the protic solvents by virtue of hydrogen bonding, by dipole interaction, or ion dipole interactions. Because this is if our nucleophile, for example, is oxygen or hydroxide, no, so it can be stabilized by hydrogen bond interaction with OH here, or something like that. Generally, we can say that there is this dispersal or stabilization of the nucleophile in the presence of the solvent. So what happens when you use a protic solvent? In the protic solvent, what is being stabilized there is the cation, no? So para dili mahilabtan si nucleophile. In this case, pag protic solvent, mahilabtan si nucleophile, and you have to remember that it is the one that will attack the substrate for the reaction to occur. Okay, so molecules of the protic solvent, water solvates a halide ion by forming hydrogen bond state. Hydrogen bond, generally, let's just say hydrogen bonds. Okay, next. So hydrogen bonding with the protic solvent. Hydrogen bonding with the protic solvent, such as ethanol or alcohol, encumbers a nucleophile and hinders its reactivity in the nucleophilic substitution. In a protic solvent, protic, so meaning there is, you will have an idea, protic, you have a proton involved, like water, methanol, no, ethanol. So in solvents like that, the general trend in nucleophilicity is among In nucleophility, ang magdahilid ions is as follows. So, baliktad siya, no, when we are dealing with protic solvents. The more nucleophilic is the iodide, the larger one, and the least nucleophilic is the fluoride, the small one. Why man? Because you have to remember that the smaller it is, no, it can be easily baliktad. It can readily form hydrogen bond interaction. No? It's not easy for protic solvents to interact with a larger ion. So dili kay siya ma-stabilize kay lisod man pagduol na because it's a large substance, a large ion. So there is a certain distance between the iodide and the solvent. No? But when we are dealing with a small ion, like fluoride ion, it can be easily dispersed, can be easily stabilized in the presence of a protic solvent, like water or methanol, because it is a small ion. And because of that, when this is being stabilized, the smaller ion is being stabilized in the presence of protic solvent, then it will become less available or become less reactive to the substrate. So there will be less reactions compared when we are dealing with a larger ion here. I hope that you're taking notes, but that's what I was saying earlier. So baliktad ang trend when we are using protic solvents. That's when we are using a protic solvent. So the same effect holds true when we compare sulfur, nucleophiles, and oxygen molecules. So if you notice, sulfur and oxygen can check on your periodic table. Okay, please check on your periodic table. Remember always to save a periodic table just in case we forget now how the atoms are arranged in the periodic table. Sulfur is a larger atom than oxygen. Okay, sulfur, and hence they are not solvated as strongly in protic solvent. So they are not solvated. So compared here, chlorine being small, its term is solvated, no? Solvated by the solvent, protic solvent, because they're very small. But when we are dealing with a larger ions, such as sulfur, for instance, no, it's not easily solvated as that when we are dealing with oxygen. So therefore, in the presence, or how can we say, RSH, the one contains sulfur, are stronger nucleophiles than ROH alcohols. Okay, in the same way, when we are dealing with RS minus, the conjugate base of the RSH, I hope you can see my cursor, no? And the ROH, the conjugate base, the one with the SH are stronger nucleophiles than alcohol. Of course, okay, this is when we are using the protic solvent because of again, sa tong term, solvation effect. Thus, the smaller the ion, the greater is the solvation effect. So when there is greater solvation effect, then the nucleophile will become less available. And when it becomes less available, then the reaction will be much slower in protic solvent. Will be much slower as when you try to compare it for a nucleophile, which is a large, which contains a large atom. I hope that it was clear with you.